Hello, I'm Aaron Armstrong, and I'm going to be talking today about the Mamba-2 architecture. We're going to look a little bit at the what and why of Mamba-2. We'll look at the architecture itself, and we'll look at two algorithms, the state decay or segsum algorithm and the SSD algorithm at the core of Mamba-2. All right, so let's start with what and why. So Mamba-2 is a algorithm that takes an input sequence and converts it to an output sequence of the same length. And as it does that, it looks at the input in blocks. So it looks at a chunk of the input, and then it looks at the next chunk and the next chunk. For each input token, it produces an output token. And as it goes, kind of like a recurrent neural network, it maintains a fixed size hidden state. So it looks at a token, computes the hidden state, produces an output, and moves through the input in that manner. It's very GPU efficient. That's one of the big improvements since Mamba-1. And it has lots of familiar elements that you might be familiar with from other machine learning algorithms. It uses a bunch of matrices for linear transforms. It uses the swish or CLU activation function. It has multiple heads, kind of like transformers, multiple attention heads. It does per channel convolution of the input sequence to kind of smooth out the signal and bring information from the local window into the current token. And it uses group normalization. All right, why does Mamba-2 matter? It matters mostly in contrast to the way Transformer works. It's intended as an improvement in some directions on Transformer. With Transformer, the compute is quadratic. When you train over a long sequence, you end up with n squared compute, and then you end up with giant GPU farms, and it's very expensive. The memory use in Transformer is linear, so you need to remember a little bit of information for each token you process, and that works okay for kind of short runs of text, but it's not at all okay if you're trying to do machine learning over genetic sequences, which might have millions of base pairs. So by contrast, this is kind of the key one, Mamba-2 uses constant memory, which is nice to keep your to be able to continue to do inference even over long sequences, and compute is linear, so it's not so exorbitant to do training. All right, there are some concerns with this architecture though. The fact that you're using a constant size memory does limit a bit the expressiveness or the complexity of the problems that Mamba can solve. And the paper walks through a bunch of different benchmarks, and Mamba is very capable, so most problems can be addressed by Mamba. But there are some problems that inherently require all the information on the table at once to solve. You can work around that a bit by increasing the size of your constant, because you're using a constant amount of memory. Maybe you could use a large constant amount of memory. You can also mix Mamba-2 blocks with attention blocks using the transformer architecture, and so you can get kind of hybrids where you have some layers that can see the whole problem and some layers that are processing with a constant size memory. So that's the main theoretical challenge. There are a couple of more practical issues. One is that the exposition and code in the Mamba paper and the related code base are quite complex. Unless you've got a strong background in control theory and numerical programming, you'll probably have difficulty understanding what's going on. The Mamba architecture has been vetted up to substantial models, up to 7 billion parameter models, but none of the frontier labs has used it to train a really, really big, maybe a trillion parameter or larger model. So it'd be nice to see some evidence beyond the multi-billion parameter models that Mamba continues to scale as well or better than Transformer. All right, here's a bit about the Mamba-2 architecture. And you can see a little key over here. We've got a couple of non-linearities, particularly the swish activation function. I have a couple of algorithms, the state space duality algorithm and convolution. And then you've got a series of matrices which are learned. And so the way this works is you start with an input, say an input token, and then you multiply that by a learned matrix, and that produces, in this case, the output, the kind of the transformed input token, which goes into the algorithm. So you've got kind of a sequence of input tokens at with a higher dimensional space. You've got a decay matrix, which is basically telling you for each input how much do you decay the existing state and how much, and that so you basically forget parts of the old state based on what you're seeing in the new input. You've got a couple of matrices, kind of like the key and query matrix in the attention or in the transformer architecture. And so you produce those, and you also create a volume matrix. And so this path of the algorithm basically allows you to learn how much volume to give the output coming out of the core SSD algorithm. So you do this element-wise multiply. And SSD takes the input and you convolve it, and that goes in, and then you take these kind of multiplier matrices and a set of decays, and you produce an output sequence, and then you do a group norm to kind of clean up some of the output channels, and then you do one more learned matrix to convert that to the output sequence. So that's the Mamba architecture, and we're going to dive in a little bit on some of these particular algorithms. Per channel convolution, the idea here is that we're trying to kind of smooth out the signal and acquire or mix in some information from the last few tokens you've seen. So if you're computing the input sequence for token 5, you're going to look back over the last typically the last 4 tokens. You multiply each of those by a learned kernel, you add them together, and that's the actual token that you send into the SSD algorithm. And so there's a little bit of, kind of gather useful information from your local context. All right. Well, many people know PyTorch, many people do not. The algorithm's code is all written in PyTorch, and so I'll give you a quick intro to PyTorch, and there's a lot more to learn there. But originally there was a C++ version of Torch, which is basically a library for doing linear algebra and machine learning, and then they ported it to Lua, and then people realized that Python was a lot more used, so they moved it to Python, and I think this is where Meta kind of picked up the development. And then they folded in, Meta had another framework for machine learning, and they kind of folded them together and came up with PyTorch 1, where it was good enough to do production machine learning. They open sourced it a few years later, and then in PyTorch 2 they added an optimizer so the system would look over the graphs you designed and further optimize it for faster computation. PyTorch is all built on top of tensors, which you can think of as multi-dimensional arrays or multi-dimensional matrices. These tensors have various dimensions. You can see that this is a 3x2 matrix. Here's an example of a 3x5x32 tensor. And so the shape refers to the set of sizes. So it tells you how many dimensions do you have and how many entries do you have in each dimension. And you can do things like reshape a tensor. So you might start out with a tensor that's 3x5x32, and then you could split this into 2 dimensions, a dimension of length 4 and a dimension of length 8, And so you haven't really changed the numbers in there, but you've changed the interpretation or how you index it. There's also squeeze and unsqueeze operations. Squeeze basically gets rid of any dimensions that have a length of 1. Unsqueeze allows you to insert a dimension of length 1 into a tensor. So you'll see that in the code later. You can also index into a tensor, and there's zero-based indexing, so you can index, if you use index 0, you're talking about the first dimension of a tensor. Index 1 is the second dimension of the tensor. And the third would be, you're indexing into here and so forth. You can also index with negative numbers. If you do that, you're starting at the back of the tensor and indexing in. So this is -1, -2, -3, -4. Dot, dot, dot is like a greedy match. So if you're trying to refer to a particular dimension, you can say, hey, I'm going to use dot, dot, dot to match all of the higher dimensions. Maybe here, dot, dot, dot would maybe refer to all of this up here. And then colon says, hey, I want all the numbers in this dimension. And then sometimes when you're reshaping, you might see the value none. So here, we're reshaping a tensor, say like this, and we match the dot, dot, dot matches the 3 and the 5, and the colon matches the 32, and then the none says we want to insert a dimension of length 1 above the 32. So you'd end up with a 3, 5, 1, 32 tensor. Tensors have data types. Each of the elements could be a Boolean, which we'll see in the algorithm, or you can have ints or floats. You can do Google Brain floats, so you have more range. They can be stored on different parts of your system. They can be stored in CPU's memory. They can be stored on the GPU or the CUDA, in CUDA memory. XLA, accelerated linear algebra, that's for Google TPUs. And MPS, metal performance shaders, is basically if you're developing on a Mac with Apple Silicon and you want to use Apple's metal system to accelerate. Last concept from tensors is this idea of broadcasting, and that's where if you have a tensor that is kind of lacking a dimension, or you don't have enough numbers, you can still add or multiply or perform operations against other tensors. So if you want to add this tensor and this tensor, initially it's saying, hey, it's kind of weird. We got this dimension mismatch. We don't have two numbers along this second dimension. So broadcasting says, hey, that's okay. Every time I need a number in this dimension, I'll just repeat the one number I do have. So if you add these two tensors with broadcasting, it'll be 1 plus 7, so you get an 8, and then 4 plus 7, and you'll get an 11. So you get two numbers in this row, 8 and 11, and it would continue. So you'd end up with a 3 by 2 matrix where the 7 has been added across each of these and the 8 across each of these. All right, so there's lots more to know, but that'll get you at least through the code we're going to talk about. Einstein notation gets used in tensors. It's basically a way to add, reorder, or multiply tensors together. And Albert Einstein developed the notation because he was working on general relativity and he was writing sums way too much. And it was driving him crazy, and apparently it was driving his printers crazy because they were using metal type and they were running out of sigmas to write all of his sums. I'm like, dude, you got to do something. You're using too many sigmas. So he came up with this idea. It's like, hey, what if when I'm doing a summation, I don't actually write the whole summation, I just write the indexes. And so you can see a few different parts. Here's a few different examples of Einstein notation, and this is the notation itself, and then this is effectively what it means. You can see the arrow here says, hey, we're going to start with some set of inputs, we're going to get some outputs. Comma basically separates tensors from each other, so this takes one tensor and another tensor, basically two vectors in this case, and produces some output. If you see nothing in the output, that basically says everything you saw over here, contract it together and produce a scalar. This is an example of a transpose where you start with a matrix indexed by I and J, and you output, you kind of reverse the numbers. So if it's, in the 3-2 position, it comes out in the 2-3 position. Here, this basically adds all the elements together. So you kind of go through each index, pull out each scalar, add them all together. If you want to do a dot product with a comment saying, hey, there's two tensors which each have a single dimension, and you take the I and the I here, you multiply them together, and then you add everything up and produce a scalar. If you see the same dimension repeated on both tensors or in more than one tensor, it's basically saying that you contract the tensor along that dimension, or basically think multiply and then add up. So here's an example of matrix multiply. You can see the repeated k, so it's saying, hey, match up the k's and multiply them together and add them, and you're still going to have two dimensions, the I and the j, but you've contracted along the k dimension. And there's more stuff in here. You can extract diagonals and do all kinds of fancy stuff. Here's element-wise multiplication. So it's kind of different here. You can see sum all, and this is you can see that you are multiplying but preserving each number independently. So you can look more at that chart, but that's the basics of Einstein notation. All right, so we're going to look at two algorithms at the core of Mamba. One is a simpler one. It's the idea of state decay. So over time, every time you see an input token, you calculate a decay factor, and you take the state that you have so far and you multiply it by the decay, and it gets smaller generally. You typically don't amplify it, so you're typically reducing it. And so the state from further back in time gets smaller and smaller and smaller. And so if you're trying to do this in parallel, you want to be able to take the state from a long time ago and add it to the state from a little while ago, and more recently, kind of that whole sequence, and kind of calculate what the current state is based on multiplying decay factors times each of the intermediate states. So that's effectively what we're doing. So here you can see that if we're calculating, if we get input token 4, we do a projection, we calculate a decay factor, and we apply that decay factor to the state as it was in time 3. And kind of similar as you go further back, the state in time 3 has been decayed by this decay factor times the state as it was in time 2, and then each input adds additional information to the state. If you look forward, effectively what we want to do is we want to calculate the product of all of the decay factors from the beginning of the sequence up to the current spot. And so this matrix represents that. Now, one thing that's a little bit funky is we're actually going to work in log space rather than a normal space. So the idea here is if you have a product of decay factors, if you take the log of that, then you get the sum of the logs of all of those decay factors. And it makes it more numerically stable to work in log space. So here, effectively what you can see for this entry in the matrix, this is saying that if you want to find out the contribution or how much you decay the state from time 0, if you want to project that into up to the present of time 3, you need to multiply it by the decay factor from time 1 times the decay factor for times 2 times the decay factor for time 3. So in log space you're adding rather than multiplying, but that's basically the product of the decay between time 0 and time 3. If you look here, you don't have as many decays between 2 and 0 as you do between 3 and 0. So you just have the decays from time 1 and time 2. Here you only have this one decay. Here no time has passed at all, so there's no need to decay the time. And you might think, oh, zeros, like I'm going to multiply by 0, that's going to be bad. But remember, we're in log space. So each of these zeros, once you exponentiate that, e to the 0 is 1. So you're really multiplying by 1. So it's saying don't decay the state at time 0 that you get from time 0. So that's what the zeros mean. That's what these sums mean. Out here, what we're looking for is we want to preserve causality. So the input or impact at time 0 from time 1 needs to be, so negative infinity in log space, you exponentiate that, and you get a 0. So there should be no impact on time 0 from time 1. The future isn't allowed to influence the past. So all of the entries out here in log space are negative infinity. All right, so that's the matrix we're trying to build up. And I'll jump ahead for a second. The code kind of looks like this, and it kind of looks like a mess. So let's walk through it kind of bit by bit, and we'll get a better understanding of how we actually build that matrix. So the first thing what we start with is this decay vector, decay from 0 and 1 and 2. We do a cumulative sum on that, and that's a standard GPU operation that it can do very efficiently. So you get the 0th factor and this, first 2 factors, first 3 factors, first 4 factors, and so forth. Then you take this vector, you lay it out this way, and then you subtract off the same vector laid out this way. So that's a little bit mind-bending. But if you look here, D0, D1, D2, and D3, you subtract off D0, then what you're left with is D1, 2, and 3. So that's this minus this kind of coming out of column 0. If you look here, you can see that this vector, this value here is basically this sum, but you take off, it's this, this sum starts out as this sum, and then you take off the first column sum. So you're basically subtracting the vector by itself, and you can see that on the diagonal it's 0 because you're subtracting by itself, and then out here you're further out in the vector versus here, and as you kind of move this way it uses more and more, it subtracts off more and more until it matches. So that's the basic idea of kind of the lower triangle. And then up here you actually end up with negative sums, which is kind of a mess, so we need to blow this away and replace this all with the negative infinities that we're trying to get corresponding to the preserved causality. So to do that, we want to fill this area with negative infinities, so we're going to make a little mask where this is all true, and then we're going to do, there's a fill operation that says fill, put in a value where the mask is true, and we can fill this part with negative infinity. All right, so now we can look at the code and kind of understand what's going on. So cum sum basically gives us this, a cumulative sum of the decay factors. And we're summing along the -1 dimension, the last dimension, because in general we might be doing this for a bunch of batches and stuff, so there's a lot of kind of higher dimensions that we're not going to sum along. And then here, this is kind of that, subtract off the vector, against itself kind of in a square way. So the first part of this is saying, hey, match all of the higher dimensions and then take the last dimension and then stick in a dimension of length 1 at the end. And we're going to subtract off all the dimensions in the last dimension, and we're going to insert a higher a dimension 1 in of length 1. And so that kind of gives you this, or is it here? basically this triangle where we've got the cumulative sum vector this way subtracted by the cumulative sum vector this way. So this is the one higher dimension, this is the last dimension. And so that's what this code is doing. Then here we're pulling off, so the shape gives us the array of lengths of the tensor. We're taking the last one of that, so it tells us how long the decay vector is, kind of the length of the input sequence. And then we make a vector that has all trues in it. And so it's a square matrix in the, with the same value in each direction. We put it on the same device that the state decay vector's in. Maybe that's on CUDA or something like that. And it's d-type Boolean, so these are all Boolean values. They're all 1, so that's true in Boolean. So this is a all true matrix. We use this here. So this is an operation that takes a triangular matrix, an upper triangular matrix, and it starts with the all true vector and keeps all of the stuff that's above the diagonal. It's 1 up from the diagonal. So if that diagonal was 0, then we'd start here, but with 1 we're going to go 1 in from the diagonal. So it's basically all of this. It's basically all of this is true. And then everything else is a 0. It's still Boolean, so those are all false. So at that point, we've got a matrix that looks like this. Okay, so now we've got our upper triangular true matrix, and then we do a mask fill. Everything where it's true, we put in a minus infinity. So we go from this matrix with stuff here that we don't like, and we fill with minus infinity along this upper triangle, and so you get your minus infinities in here. All right, so that's what this code is doing in kind of this fancy GPU optimized way. All right, so that's segsum or state decay. Now we go into the SSD algorithm, which is kind of the real heart of Mamba. So you can see it here, kind of all the stuff funnels into SSD. So it's our state space duality, or kind of sequence transforming algorithm. So here's the overall view. The code itself is pretty tricky when you first look at it. I think the biggest thing I've changed in this presentation, I've tried to give kind of clearer names for each of the things. The original code, it's all like single character letters, and so it's a little bit challenging. But you have your input sequence. It's been convolved already, and it went through a swish. But this is your input sequence. You've got your decay vector we just looked at. You've got two matrices that help you kind of work on your input and your state. They kind of work like the key and query matrix in transformer. And you've got some state, and in training your initial state is 0, but for inference you'll calculate a token, and then your output's final state becomes your input state for the next token, and so you just keep passing it along. So these are all your inputs. You start out by reshaping stuff, so you're basically moving from a long sequence to blocks of input, because we'll process block by block. That's where we get a big speed up in Mamba-2. We calculate our decay matrices. That uses the segsum algorithm that we just looked at. And then kind of the core of the algorithm is we're calculating the output on a per block basis, and we'll go into this more, but we're calculating the output kind of across blocks. And then they do some careful math in the paper to show that you can decompose. When you decompose the system this way, you can add the per block output and the cross block output together, and that is equivalent to kind of processing token by token. And so it's mathematically correct, but you get this, large constant speed up. Maybe your blocks are 64 tokens long, so you can get a factor of 64 improvement in the parallelism. So you calculate your per block output. You calculate your per block state. Here you take care of if you don't have any state to start with, you initialize it to all zeros, and then you put the initial state in front of the state you've gotten per block, and then you calculate your cross block state. So now you're kind of seeing the state kind of across the whole sequence. Once you have all of that state, then you can calculate the state kind of coming from each across each block, and then you can sum those. You take the cross block state, you pull off the end of it, and that becomes your final state. Once you have the sum, you reshape it so that it goes from kind of the block by block back to the kind of single long sequence, and then you output that. So that's the kind of the big structure of the algorithm, and then we'll look at each bit of the code here. This is a breakdown of the code. Uses a lot of Einstein sums, and the indexes are, by convention, they're single letters, which is a little bit hard to keep in your head. So if you're like, hey, I don't remember what B and C was, here's the decode. You can look at this later. A couple of the dimensions are the same. Z and C are the same, but Z is talking about stuff where it's an output, and Z is talking about where it's an input. Sometimes you need to distinguish that in the sums so that you don't contract along dimensions you don't want to contract along. So at the beginning, we got to reshape the blocks. So here you can see we go through each one, and we're basically saying the second dimension here, which is the sequence dimension. It starts out kind of one long sequence, and we want to split that by the number of tokens per block, maybe 64 tokens per block, into chunks. So you've got the top level index, you're indexing by block, and then this is the index within the block. Here we're rearranging. We're basically the input by convention. Typically you list the heads, the decays on a per head basis, but for the computations we're actually going to do, we really care about the number of blocks and the index within the block. So we're going to iterate over these, so we push the head dimension up higher so we can basically ignore it in the sums. All right, so then we calculate each of the decay matrices. These all get used at different stages of calculating the state or the output. And so you can see here that we call the seg sum or calculate state decay matrix algorithm that we just looked at. We give it the state decay metric vector, and then we exponentiate to go from log space back to normal space. And you'll see that a bunch of places where we do this exponentiation to get back to normal space. So here we are doing a cumulative sum of the state decay vector, so you get that kind of looks like this. That's your cumulative sum. And then we exponentiate, so we have a cumulative product. So we're back in normal space, and we use that to calculate changes in state. And then here we're doing a similar thing as in the seg sum algorithm. You can see that we are all right, and so then here it's very similar to the seg sum algorithm, where we are subtracting off cumulative sum bits. Let's see. So what we're seeing here is we take the highest dimensions, we take the last dimension, we insert one more dimension, and then so this is a dimension of length 1, And as we talked about, we subtract off the cumulative sum here. And what we're getting out of this is the sum of the decays from the k plus 1th step up to the nth step, basically within the block, all of the decays up to the end of the block. So we use that when we're calculating per block state. So you want to see kind of at the end how much did this contribute, and so you need to have the decay factors from the time you calculated it out to the end of the block. So that's effectively what's happening here. This one, you got your exponentiation to go into normal space. This fpad stuff is basically inserting 1 0 at the beginning of the cumulative sum and 0 zeros at the end. So more or less like put a 0 at the beginning of this, and if you remember we're in log space, so that 0 when you exponentiate becomes a 1 in normal space. And so what we're doing is we're saying at the end dimension, at the last dimension, put in a 1, which more or less is saying we're grounding the sequence of decays by multiplying by 1. So don't your first input should not be decayed when making your first state. That's effectively what's going on there. And so then you can use that for calculating output. All right, so you get a bunch of decay matrices. When you're calculating per block output, this is pretty vanilla. You're basically multiplying all the things together. You start with your input, and you multiply that. You decay the input by the state decay matrix, and then you apply the input key matrix to figure out what parts of the input you care about, and then you multiply by the state query matrix that's kind of pulling out the relevant bits of state, and so you get kind of chunks of output kind of within each block. And then you want to calculate the per block state. Fairly similar here. You're starting from the input. You calculate. You just saw how we calculated the decay factors from the k plus 1th decay factor up to the end. So that decays the input sequence. And then the input key matrix is saying what parts of that input are important for the state. So we're pulling that out. This is handle the initial state. If you don't get any state, we make some state. It's all zeros. And this stuff is basically saying, let's slice up this tensor so we get one block. Basically, it's length 1. So the state per block, this is kind of has the whole sequence of tokens within the block, or this, states within the block. So this is like, hey, we want one that's 1 long, not n long. So that's if we don't have any state. If we do have state, the state's coming in the wrong shape. So we're reordering the initial state. So we do this permutation, and effectively what's going on is we're flipping the head dimension and the state dimension because the input doesn't match the way we're actually going to be computing inside. And then this unsqueeze inserts a 1 long dimension at the first position. So that 1 is the first position. So basically is saying we'll have a dimension along the block. In the block dimension, this will be 1 long. And so we get the state in the right shape to interact with the rest of the state. So then when we augment it, this torch cat basically says, hey, take this state and this state, turn it into one new tensor, and we're concatenating along the first dimension, the block dimension. All right, here, calculating cross-block state. This is a fairly straightforward sum, we're taking the state decay matrix across the blocks and the augmented state per block, and so we get the state across the blocks. Now we've got the state, kind of basically the final form state. So we need to pick off the kind of what the final state will be like. So we don't want all of the blocks. We just want the kind of the state from the last block. And then this permutation is putting it back in the order we expect. We expect the kind of the final state to be in, and then we can return that. So that's the kind of the final output of the state. And then calculating the cross block output. Here, we're basically we're keeping the batch as is. We're taking all of the state except this -1. So basically, we took the last element of that state and returned it as the final state. Now here, we're keeping all the rest of the state except that thing we sliced off to send as the final state. So we have all of this state across the blocks, and then we can multiply that. This is our state decay vector and our state manipulation or state query matrix. You multiply those together and you get the output sequence kind of across the blocks. And now you've got the output sequence per block and across block. You can add those together, and then you basically relax. We had it split up between blocks and indexes within the block, and now we can group those back together into one long sequence. And you've got the full output. So yeah, so you've got some reshapes, some decays, per block output. You calculate some state and cross-block state. You get your cross-block output. You sum them together. You reshape everything, and you return the final state and the final output. So that's the core of Mamba, and hopefully, if you're looking at, I'll post my implementation with the kind of more descriptive variable names and flow. And hopefully, if you need to, you can use my implementation and go back and read the paper and understand what the paper is talking about with all the cryptic names. So yeah, so that's Mamba-2. Any questions?